represents a period in Earth's history from 4 billion to 2.5 billion years ago. While the end of the so-called Great Cometary Bombardment of the Earth, while the end coincides with the Great Oxygenation Event, when the fundamental nature of the Earth's atmosphere changed forever. The beginning of the Archean was marked by the end of a bombardment of Earth by comets or asteroids. Determining the positions of continents and oceans at this distance in time is an extremely difficult business. Very few rocks of this age remain, and those that do have, in many cases, been profoundly altered. Indirect evidence for the earliest rocks comes from crystals of the mineral zircon, eroded from granites and redeposited in younger sedimentary rocks. These formed during the early Archean, or even in the preceding Hadean period. The oldest of these is a single crystal from Western Australia that has been dated as more than 4 billion years old, which supports the argument that at this extremely early period in the Earth's history rocks were crystallizing, slabs of continental crust were forming, and, just as significantly, there was water on the planet. However, it may not have been until about 3 billion years ago that a land mass of any appreciable size was formed. Before this, fledgling continents probably came together and were then rapidly eroded or subducted, leaving only a few traces in the rock record. The first continent from which rocks still exist has been called Ur. It comprises the ancient Cratons, also known as Shields, Od Central Southern Africa, the Pilbara region of Western Australia, India and small parts of Antarctica. About 500 million years later, at the end of the Archean, a second continent called Arctica formed, consisting of the Cratons of present-day Canada, Greenland and Siberia. Reconstructing the position of these early continents on the globe is very difficult. During the late Archean, Ur may have been situated in high altitudes, whereas Arctica was in low latitudes. The Archean oceans are likely to have been more extensive than they are today because the continents were smaller. They also differed from modern oceans in that they were about 1.5 to 2 times more saline. Moreover, they were devoid of dissolved oxygen. The only life that oceans could support was in the form of single-celled organisms, probably anaerobic bacteria and archaea, which do not require oxygen. Evidence for their existence comes from fossils of filamentous bacteria and structures called stromatolites found in rocks as old as 3.49 billion years in present-day Australia and South Africa. For much of the Archean, the Earth's atmosphere is thought to have been devoid of oxygen. Instead, it was composed primarily of nitrogen, methane and carbon dioxide. The Sun was much weaker then, emitting less radiation, so had it not been for these greenhouse gases, the world would have been a ball of frozen rock. In fact, research indicates that an atmosphere rich in greenhouse gases helped create extremely high global temperatures. Especially early in this period. These could have been within the range 55 to 88 degrees Celsius. Ocean temperature would have been correspondingly high, and the only forms of life capable of living in the hot, salty seas were thermophilic anaerobic bacteria and archaea. Although the climate was very hot overall, about 2.9 billion years ago temperatures appear to have fallen drastically for a relatively short time, and the Earth may even have experienced its first glaciation. Geological evidence suggests that during the last few 100 million years of the Archean temperatures returned to their previously high levels. Any life forms that may have lived in the Archean were likely to have been very tough, and very small, like modern N-bacteria and Archaebacteria. Recent work on the DNA of these modern forms has shown that they are probably the most primitive of life forms found today. They are known to use the energy stored within the rocks and minerals of the Earth as sources from which to create the basic building blocks of life. Fossils from this period are very rare, but of supreme importance for our understanding of how the Earth became a habitable planet. Some of the earliest evidence for cells in rocks of the Archean comes from South Africa and Western Australia. These ancient rocks, dated to 3.49 to 3.43 billion years ago, show that simple bacteria were probably living in settings lacking in oxygen, but high in silica and metallic sulfides, especially volcanic environments. Recently, tiny tubular microborings, which may well have been produced by bacteria, have been discovered in basaltic pillow lavas. In Sulphur Springs, Australia, slightly younger clusters of thread-like fossils preserved in iron sulfide have been found. The deposits are about 3.2 billion years old, and comprise sulfide-rich cherts that formed around submarine hot springs, much like those of modern black smokers. The fossils themselves comprise tiny cylindrical threads about 1 micron wide, trapped between layers of iron sulfide that may have formed part of a black smoker chimney. A second line of evidence is from stromatolites. Microbial stromatolites often form distinctly crinkly layers, and stromatolites of this kind have only been found in the rock record after about 3 billion years ago. Some of the most ancient examples are known from the Strelly Pool chert, dated to about 3.43 billion years ago, although these do not show the crinkly layers consistent with a microbial origin. It is only after about 2.6 billion years ago that cyanobacterial fossils appeared, but it seems to have consisted largely of forms living on the enormous supplies of internal energy from the young Earth.